Hello everyone, this is the second episode of LOFAR Solar and Space Weather Data Workshop, and so this episode is about interferometric data, the measurement set file and its inspection and pre-processing. And this episode will include a demo session, which is a quick walkthrough of everything from downloading to inspection and calibration, and until we get to the step of clean. First, download the data from a long time archive. It has a link like this, and after that, enter and rename the files and folders into a more organized form. There is a script doing this job quite well. It's very simple. Just put this script into the folder where you download the data, and after that, run this Python script, and it will do all the work. After that, we need to do a little inspection to the data to see what is inside this measurement set. There are two very handy tools to do this job. One is MS Overview, another is Casa Browser or an Casa Browse Table. So after that, we know enough about the data set. We will do the pre-processing, including maybe auto-weight if if the auto-weight is not run before, and predict cal and apply beam and apply cal to basically use a reference astronomy source to correct the flux and phases of the solar observation. So next is the demo session. So first of all, we need to go to this long time archive to stage our data, browse projects, and find the project. For example, we need solar observations, for example, this, and show data. And all observation pipelines, there will be many data sets, and we can see this, and maybe one of them, and do the stage selected. So as you can see, I selected one file, and it's 78 gigabytes. It's quite large, and if I click submit, I will soon receive a email containing the direct links to all of the files. It's html.txt, and as I already download everything, I'll show this html.txt. These are all the direct link to these data files, and to download the file, you need to just wget dash c. C means continuous, and I means input file, html.txt, and after that you can download everything. After download, you will have this huge amount of very long name data files in your folder. And recall what I just mentioned on the script. So for convenience, I put all the script to this Git repo, and we can use everything from here. So let's git clone this repository to local folder, and after that there will be a folder named represent tools, ls represent tools. Yeah, these are the scripts and code for pre-processing. Here we copied the old row, scratch, pipe, everything to current directory, and we have a few scripts. So first step is do the enter and rename. So here we just run this Python script on tar. It may take a while. Okay, finally it finished untar and rename everything. Let's see what is now in this folder. As you can see, the long name is cut it into a very short name. And as you can see, everything turns to be very nice and organized. So let's see what's inside a measurement set folder. Uh, there are basically tables and subfolders. It contains all the observation information, most importantly, the correlation intensity. So let's check what is in this measurement set file. In order to inspect the data, we can do either MS Overview or Casa Browse Table or Casa Browser. Let's do both. So in this folder, I have a lot of measurement set files. For example, this one. Let's do MS Overview in equals this file. It will show the detail of this observation, the name, a directory of this measurement set, and its project name. It's observed by LOFAR, and the antenna set is LBA outer antenna set. And the observation time from here to here, the total duration is about 9,000 seconds. And the object is class A, so it is a calibrator. And the subband name and frequency channel, the channel width and total bandwidth and correlations. It has XX, XY, YX, and YY, so it has full Stokes of polarization. You can do polarization image for this period of time. But if we want more information, we can do verbose equals t. In this case, we can have more information, including, sorry, I need to shrink this a little bit to make it more typesetting better. So there are more informations about antenna name and antenna diameter and longitude, latitude, and the location and the location in another form. Also, it has all the time index and all the baselines, baseline count. There are 561 baselines. 33 of them are autocorrelation, which means the rest of 528 baselines are cross correlation. So this can kind of give us an overview of what is inside this data set, and we can do a another also we can go deeper. Also, if we want to inspect like the number of the data, we can use Casa Browser. Any file, the same file. This will open X window, and it contains a big table. UVW is a baseline, so 000 means autocorrelation. It is, for example, the first row, the 0 row. It is the correlation of antenna 0 and antenna 0. So the baseline is 000. It's a key vector. When this key vector is not 0, for example, the first row, it's cross correlation. and the actual data is in the column of data or corrected data. And it is a four-number array of complex number. It contains the correlation intensity. So this is basically a huge table, contains all the data of every frame. And if we want to do an even more in-depth inspection for the dataset, we can use plot.ms of CASA. So CASA plot.ms. This is an interactive tool for the measurement set to plot to see what is actually inside the data. So for example, we use the previous one, we just used, and we can choose the x-axis and y-axis. For example, we choose UV distance for x-axis and amplitude for y-axis. Also, we can colorize the data with another parameter. For example, we colorize the data according to time, and we can generate a plot. So this is the plot of amplitude versus UV distance. And as we can see, the UV distance goes to 25 kilometers. Also, you can choose other data field for X and Y to do your own inspection. This is a very nice tool to see all the data points inside this measurement set data. So after that, we can do the calibration. So the calibration is done with the default pre-processing pipeline, which is also known as DPCube. But I need to mention that LOFAR software has a very complex dependency. It could be very tricky to install everything and make it work. What I suggest is to use the official Docker published by Astronomy, and you can use one command to run this Docker without install anything. That saves a lot of time. So this is a demo of calibration. In this directory, there are 120 measurement set files. Half of them are the observation of calibrator, starting with the society of this, and the other half of them are the observation of the sun, starting with the society of this. So we need to use the observation of a calibrator to correct the flux and the phase of the observation of the sun. First, we need a source DB file describing the model of calibrator. It can be generated from a sky model file. The sky model file can be found in prefactor code repos. So let's get going. Here we have prefactor and CP prefactor sky models. We need 18 files, a low res to the current folder, and add 18 sky model. So in this sky model file, we have a few models of calibrators of 18. For this dataset, as we can see, we have Taurus A as a calibrator. So we need to generate the source DB from this patch of this sky model file. To do the calibration, we need to start a Docker image to have the software environment of LOFAR data processing. To do that, we need to do docker run this command. Sorry, yeah. So docker run --rm means remove after exit. Otherwise, we will generate a snapshot of Docker image. which will take a lot of storage. And the -IT means interactive terminal. It gives you a terminal to do the data processing. And -V means volume. We want to mount a volume at the directory of this containing our data and to the mount point of LOFAR data. And the last field is the name of the Docker image. So let's start this shell. And after you start this Docker run thing, you can have a interactive shell to type in your command to do the data processing. If you run this command for the first time, you will need some time to download the Docker image from the official website. So let's see, we have these files, and in order to initialize the software environment, we need to source opt and lofarsoft.sh. After that, we can have the dpcube version, and we can have ws clean. And we can have make source db. So we have what we needed to do the calibration. First step is to make the source db file. And according to the documentation, we need to specify the in and out. In is the name of input ask file, and out is the name of the source table. So we need to specify in equals wait a minute. We need to go to the directory of where our data is located and see we have everything, and then do the make source db. In equals the sky model, and out equals let's say Taurus A dot source db. And we need to still specify the patch prefix to let this command know what source we want. In this case, Taurus A. Okay. In this case, we have a Taurus A dot source db. So I have this autocalib.py script which can run the calibration automatically. Let's see what's inside this. It is a Python script, runs all of the 3 steps, predict parset, apply cal, and apply beam. So there are a few places we need to change. First is we need to specify what is a solar observation and what is a calibration observation. We need to specify that with SysID. The SysID of calibrator observation is this. So we need to change the calibrator to this. And after that, we need to change the solar observation SysID. Then we need to specify the calibrator. We use a source of tau A, not tau AGG. We use the source db of tau A dot source db. Let's make sure of that. It's tau A dot source db, yes. And the run step means the first step and the second step and the third step. Predict parset, apply cal, and apply beam. So 0, 1, 2 means run all the 3 steps means a complete calibration. And then we can run this script, and after this we can have a calibrated data set. Let's do the Python dash project. Do we have Python 3? Yes. Python 3 autocalling. All right. The calibration started. We just need to wait a lot of time until the whole process automatically run for all the subbands. Then we will have the calibrated datasets to run the WS clean to create the interferometric image and do the science. In the next episode, we will talk about use WS clean to create image fits file from the calibrated dataset.